Okay, today we're going to start our lesson on 4.3, the law of cosines. We learned with the law of sines, we're looking for angle, side, angle, 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 side, and then that ambiguous case is side, side, angle. For law of cosines, we use when we have either side, 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 or side, angle, side. This is the formula right here for the law of cosines. I try not to get too hung up on all the A, B's, and C's. You will notice that side A, and then it's cosine A. So the side over here on the left, the B by itself, would be the one that's attached to the angle for the cosine. And all these other letters inside are just the other two sides. Okay, so let's take a look at a problem here. If we're looking at a side, side, side case. So let's draw ourselves a triangle here. We have triangle ABC, and I know that side B is 12, side A is 5, and side C is 15. With the side, side, side case, you do want to solve for the biggest angle first because that will drive out any possible obtuse angles. So we're going to say, okay, we want to solve for the biggest angle. It will be across from the biggest side. So we're going to have 15 squared is going to equal 5 squared plus 12 squared minus 2 times 5 times 12 times the cosine of angle C. From here, it's just kind of whittling through the arithmetic of it all. We got 225. 5 squared plus 12 squared is 169 minus 120, the cosine of C. Subtracting the 169 over, we get 56 is equal to minus 120 cosine C. Dividing by negative 120, we get negative 4.6 repeating cosine C. And remember, since we're solving for an angle, we do need to use our inverse functions on the calculator. And I find angle C to be about 117.818. So 117.82, we can leave that at there. From there, since I've driven out the obtuse angle, I'm going to switch over to the law of sines. It's a little bit easier of a calculation. So I'm going to say that the sine, 117.82, all over 15, is going to equal sine B over 12. And just kind of remembering again, we need to use our inverse functions here. So B is going to be the inverse sine, multiplying in this direction. 12 sine 117.82 divided by 15. And I find angle B to be about 45.04. And then just subtracting from 180, we can, because all triangles sum to be 180, we find the third angle to be about 17.15. Okay, moving on to a side angle side case. Let's move this down a little bit. So I have my triangle here, A, B, C. It's telling me that side A is 10, side B is 13, and angle C is 70 degrees. You don't have to worry about solving for a certain side first when we're talking about the side angle side case. We are going to have to find side C first because this is the only angle that we have. So C squared is going to equal 10 squared plus 13 squared minus 2 times 10 times 13 times the cosine of 70. Because all the numbers are filled out here on the right side, you can just put this into the calculator in one big swoop if you want, or you could do it in pieces. We're going to get 269 minus 260 times the cosine of 70. That gets me C squared is equal to 180.075, and then taking the square root, I find side C to be about 13.42. From that point, again, I do switch to the law of sines. It's a little bit easier to solve here. I'm going to find angle B first. So I'm going to say the sine of 70 over 13.42 is going to be the same as sine of B over 13. Again, use your inverse signs. We get B to be about 65.55. And the only thing left we need to find is that third angle. And again, subtracting from 180, we get A to be about 44.45. Okay, so that's basically how the law of cosines work. Let's take a look at a couple of application problems on the back side of your page. We've got some trapeze artists here, and they are flying, and they want to know the angle in which they are going to meet. So we're looking for this angle theta sitting right here. This is a side-side-side situation that we're looking at, so we do want to solve for the biggest angle first. That will be the one across from the 26. So we've got 26 squared equal to 17 squared plus 13 squared minus 2 times 17 times 13 times the cosine of theta here. Working through all this, we wind up with, let's see, 676, 458 minus 442 times the cosine of theta. Subtracting over 218 minus 442 cosine of theta. And again, remember that inverse function we need when solving for an angle. We find theta to be about 119.55 degrees. We have another problem here. We're looking at the length of a marsh. We have a surveyor walking 300 meters. From point A to point B, and then he turns 80 degrees, so he's coming in this direction here, and he makes a turn of 80 degrees, and then walks 250 meters over to point C. We want to approximate the length of the march, so we're looking for the length of AC. The first thing we're going to need is this angle inside the triangle. 80 and that angle are a linear pair together, so this angle inside is going to be 100. This is a side angle side case, so we are definitely using our law of cosines here. And we're looking for the length across from the angle, so that would be the one that's by itself on the left. I'm just going to call that x, so x squared is equal to 250 squared plus 300 squared minus 2 times 250 times 300 times the cosine of 100. I put all this directly into the calculator, just looking like I see it. I got x squared is equal to 1785447.227, and then taking the square root from there, we got x to be 422.55, and I think we are talking about meters here. Okay, we've got a baseball problem. Those of you who like baseball. The baseball player in the center field is approximately 330 feet from the television camera that's behind home plate. A batter hits a fly ball and goes to the wall 420 feet from the camera. Approximate the number of feet that the center fielder has to run in order to catch the ball. We've got an 8-degree angle there. So again, we are looking at another case here of side angle side. We're looking for this length over here that the ball player would have to run to catch that ball. It's the side across from the angle, so that's the one that's by itself on the left. And we say, let's see, 330 squared plus 420 squared minus 2 times 330 times 420. Again, times the cosine of 8. Put all that right into the TI-84 just like we see it. Just make sure you're inputting correctly. We get 10797.691, and taking the square root, we find that the ball player will have to run about 103.91 feet in order to catch the ball. The last problem we have to do is with navigation. So we have a map here. It says that Orlando is 178 miles due south of Niagara Falls, and Denver is 273 from Orlando, and Denver is 235 from Niagara Falls on this map. We want to find the bearing of Denver from Niagara Falls. When we talk about bearing, we are talking about a turn from due north. So what we're looking for ultimately is this angle outside here. We do have a side case here, so I need to find this angle, and then I'm going to take the linear pair to it to get the angle that we're actually looking for. Remember, with side, we do need to find the biggest side first. It just so happens, or the biggest angle first, it just so happens that the biggest angle is across from the biggest side, so that will make it just a one-step problem for us. So we're going to have 273 squared is equal to 235 squared plus 178 squared minus 2 times 235 times 178 times the cosine. I'm just calling that x right now. On the left here, we get 74,529 is going to equal 86,909 minus 83660 times the cosine of x. I wind up with 2, subtracting over here, 12,380 is equal to negative 83660 cosine of x. And finally, using our inverse function on our calculator, I get x to be about 81.49 degrees, and that's the angle that's sitting inside the triangle. To get the actual bearing, we need to subtract from 180, so our angle theta is going to wind up being 98.51 degrees. And with that, we conclude our lesson on the law of cosines.